Our next speaker, Dr. Quanlin Lee. He has more than 8 years of R&D experience in the areas of two-phase flow and heat transfer and thermal fluid management system development. He received his PhD from Case Western Reserve University, developing an integrated variable conductance heat pipe for spacecraft heat rejection applications. Since joining ACT in 2016, Dr. Lee has been actively involved in multiple SBIR, STTR programs to develop cutting-edge thermal management solutions.
Quanlin Lee. Today I'm very honored to present the work performed on the STTR Phase 1 program, improve the reliability of hot reservoir VCHP. The academia partner for this program is Case Western Reserve University. All personnel involved in this program from both group ACT and CWU are listed in these slides. Okay, so the presentation today will be structured like this. I will briefly talk about some background about what is the hot reservoir VCHP and what is the advantage of hot reservoir compared with the traditional VCHP with cold bias reservoir, and what would be the challenge to design a hot reservoir VCHP. And also I will talk about the concept developed under this STTR to mitigate the challenge of hot reservoir. And the concept is called loop hot reservoir VCHP. I will talk about the concept and the physics behind this. Then I will talk about the feasibility study performed in Phase 1, including numerical model developed by Case Western Reserve University and the experimental validation performed by ACT. After that, I will make some conclusion and talk about the work plan for the Phase 2. So the motivation behind hot reservoir VCHP is to develop a variable thermal links connecting between the payload and the radiator for the lunar missions. We want this thermal link thermal conductivity should be as high as possible during the lunar day so that the radiator panel size can be minimized. During the lunar night, we also want this thermal links to be very insulated so that the payload temperature can be maintained warm and using a very small amount of survival power. Variable conductance heat pipe seems to be a very good option for this kind of applications. Basically, it's a heat pipe charged with non-condensable gas, and because of pressure balance between vapor and NCG, the active area or active length of a condenser will change according to different heat load and the sink temperature. When the sink temperature drops, the NCG will expand and cover the condenser area, and the evaporator temperature can be maintained at a higher level. The picture showing here is the standard VCHP with a reservoir attached at the end of condenser. We call it cold reservoir. And for this cold reservoir to maintain the evaporator temperature within 1 or 2 degrees, we will need some electrical power, 1 or 2 watts, to heat up the reservoir during 40 days of lunar night. And to supply this 1 watt of electricity will give you an additional 5 kilograms of weight penalty. So that's the reason we like to go to hot reservoir. And the main difference between hot reservoir and cold reservoir is that hot reservoir VCHP, you have a reservoir that is attached at the upstream of the evaporator, and the temperature of reservoir will basically follow the payload temperature, in other words, the heat source temperature instead of the sink temperature. So that will offer much tighter thermal control capability than the traditional cold reservoir VCHP, which I will show in the next slides. And also you can use the payload waste heat to maintain the temperature of the reservoir during the lunar night, so you can eliminate that additional 1 watt or 2 watts of survival powers, further reduce the mass of the system. So this is an example about how good this thermal control capability of hard reservoir VCHP. For the standard condition, this VCHP is rejecting 50 watts of heat to a 50 degrees C of sink temperature. And the evaporated temperature showing on the top of this figure is around 17 degrees. And we start decreasing the heat load from 50 watts all the way to all the way to 11 watts. And we also decrease the sink temperature from 50 degrees C to -20, so that go into the survival mode, as I show here. And the evaporated temperature, you can see, only drops by 2 degrees. So the turn down ratio for this hard reservoir VCHP is about 150. So this shows that this is a very good device for thermal link, but there's a challenge associated with the fluid management. So in 2017, we test a hard reservoir VCHP in ISS as a part of APTX with a Marshall, and the result shows that the temperature of the vapor become very hot, higher than what we expected. And the reason for that is we found the vapor actually present in the hard reservoir and push all the non-condensable gas out from the reservoir and enter the heat pipe volume. After we identify this problem, we start purging. In other words, removing the moisture from the reservoir by electrically heating the reservoir. And we found this is a really long process, and we have to shut down the experiment at the end of the flight. Based on this past ISS test experience, we learned that fluid management is a very important area to be improved for the hard reservoir VCHP to be applicable for space application. This can be divided into two aspects. One is we need to prevent working fluid entering the reservoir during the operation, start up or any operation in the space. Second, if there's a fluid accidentally being present in the reservoir, can we find a way to remove the vapor from the reservoir effectively and efficiently? This is not easy to do for a hard reservoir because the reservoir cannot be wicked. You cannot put the wick structure in the reservoir. And purging is really a challenge. As I showing here, this is the model developed by Case Western Reserve University, showing give you an estimated time for purging. If you want to remove the vapor from the reservoir, from the moisture level from 50% to 30% by diffusion only, it will take hours or even days to complete. And because there's no other way you can remove vapor, it is dominated by the diffusion of two species. So we have to figure out other way to provide a good purging process. This is the objective of this STTR program, to develop innovative fluid management features, concept or strategy. They can improve the reliability of hard reservoir VCHP so that it can be used in space for a long period of time. And as I said, Case Western Reserve University is our academia partner, and their support is from a modeling side. So the solution we come up with during the phase 1 program is called Loop Hard Reservoir VCHP, as the schematic shows in these slides. The idea is adding another NCG tube connecting between the condenser and the reservoir and forming a loop for fluid flow. In such configuration, we should be able to use the momentum, some momentum of the primary flow in a heat pipe section can transfer through shearing to induce another flow that will circulating along the loop in a favorable direction. In other words, a counterclockwise direction showing these slides. So if we can generate this kind of flow in this configuration, this flow will continuously remove moisture from the reservoir without using additional power. And we don't need additional heating element to heat up the reservoir for purging. And purging will be happening during the entire mission. We call it passive purging concept. So this is the idea of the loop hot reservoir BCHP. So in the phase 1 program, we're trying to demonstrate this idea through both numerical model as well as experimental measurement. So for numerical model, this is done by Case Western Reserve University. They developed a CFD-based model to study the complex fluid or transport phenomena within that configuration. The calculation domain is shown in this slide. It has 2 regions. One is heat pipe region. The other region is the external NCG tube length. And the model was ran by ANSYS using in-house Fortran code to assign a boundary condition in the heat pipe section. Using their model, they can calculate the pressure, temperature, and the concentration of 2 species within the heat pipe section. And using that pressure distribution, they can also calculate the induced flow within the external loop. So here just shows some example of what they calculate. Figure on the left is the pressure distribution within the heat pipe section at the end of condenser. Figure on the right is the velocity profile within the heat pipe section. As you can see, there's a non-zero flow actually at the outlet of NCG tube, showing that there's a flow actually can be induced by this momentum transfer concept. Figure on this slide shows some parametric study performed by CFD model. Figure A shows the influence of the length of an NCG tube in the heat pipe section. When the NCG tube increase and go into the condenser, the induced flow velocity will decay. And the figure B actually shows the relationship between the power and the momentum induced flow in the loop increase as the power increase. So their conclusion from CFD analysis is that it is possible to generate non-condensable flow within the loop BCHP by momentum, but there are multiple design factors need to be considered to obtain the flow, including working fluid and NCG pair, the thermal physics property of their selection, and the power and operating temperature of the heat pipe. As I said, the location of internal NCG tube length is very important, and the relationship between the NCG tube outlet and the vapor NCG front location. So in phase 2, we will do a more detailed systematic study to maximize the flow. So in parallel, ACT trying to demonstrate the concept from experimental side, and we come up with experimental setup like this to capture or dictate the flow generated by the momentum of the primary vapor. So as you can see, we use a flow meter connected in the external loop to capture whatever happens inside this loop and see whether we can capture the flow. So before we do the flow measurement, first we want to validate that adding additional NCG tube at the end of condenser will not compromise the thermal control capability of the hot reservoir BCHP. So this is the test result we did. The power was 80 watts constant during the testing. And at 2020 seconds, we suddenly dropped the sink temperature from 75 degree to minus 10 degree. And the evaporator temperature only decayed by 10 degree. So this shows that we still have a very good thermal control capability with the loop configuration. But the focus of this program is about flow. It's about fluid mechanics within the hot reservoir BCHP. So I'm showing you this test result, signal capturing by the flow meter. So the figure on top is the temperature history, and the figure below is the flow meter signal. When there's a front established in the condenser, we start obtaining some signal from the flow meter, and that signal is actually oscillating. And the reason for the oscillation is caused by bubbling within the evaporator, because there's some puddles and there's some slugs formation in the condenser that could causing some pressure wave, and pressure wave will propagate in both directions, causing that oscillation. And when the valve is closed, we have a valve between the loop, and when we close the valve, the oscillation amplitude become larger because the pressure wave actually propagate in just one direction, and the gas flow meter will experience a full amplitude of the pressure wave. So this is not good for us, because we want to measure, what we want to see is a continuous induced flow, and that could be embedded within this oscillatory flow. We call it AC component. So in order to minimize the effect of that oscillation within the measurement, we need to minimize our fluid charge. This is the data, the flow data capturing with a different fluid charge. As you can see, when we reduce the amount of working fluid, the amplitude of that oscillation decayed significantly. So by this way, we should be able to see the DC flow. So this slide shows the DC flow capturing by the flow meter when you increase the heat input. The red line is actually the power input, and the blue line is the flow signal, and the darker one is the moving average. So you can see there's a clear relationship between the power and the induced flow, which is small, but it should be dominating the diffusion purging process. So after we demonstrate that a flow can be generated by the momentum, we start develop a prototype that using this concept. This prototype has a reservoir integrated with evaporator, just like what we did for the ISS test. And we also use a flow meter to capture the flow. This is the test result with the prototype about the flow. At different power, we can see the flow actually increase. So next step for this program is to identify how can we increase the flow, and what is the relationship between the flow and the purging. So the key takeaway of today's presentation is that hot reservoir VCHP is a very good variable thermal links for planetary landers compared with cold reservoir, because it can provide much tighter thermal control capability. But there's a significant challenge to design hot reservoir, especially the fluid management side. And in this phase one, we developed an idea using the loop to generate a momentum that can help purging. And this concept was demonstrated through both numerical model and experimental validation. And we also identified that the flow behavior within the loop VCHP is actually pulsating. Maybe we can use that pulses to further increase the flow. That will be some work will be performed in the phase two. So the future work for this phase one, for the phase two, is further study the flow, master the flow, and maximize the flow within the loop VCHP, and use that flow to significantly increase the purging rate. This is the prediction comparison between the diffusion-based purging and the convective-based purging. If you want to reduce the vapor concentration in the reservoir from 50% to like 35%, only rely on by diffusion, it will take 24 hours. But if it can generate a small amount of flow, like 0.5 millimeter, the time for purging will significantly shorten. So this is our goal. We want to increase the flow and minimize the purging rate, minimize the time for purging. So last slide, I would like to thank the support from Marshall Space Flight Center. The program is funded by STTR, And thanks for the technical support from Technomonitor, Brian O'Connor and Jeff Farmer. And also like to thank the technical support from ACT, Phil and Chris Jamoski. And thank you for your attention. I will start taking questions from here.
Thank you, Dr. Lee, for that presentation. Bill, do we have any questions coming in?
Sorry about that. Let's see. We've got sorry, I have to refresh the feed on the chat here.
Yeah, no problem.
I don't see any, but let me double check. I've had to refresh my the feed on the live stream quite a few times to get it to update.
Yeah, and folks who may have just tuned in fairly recently, just note that there's about a 20 or 25 second delay on the live stream. So.
Okay. Well, I just had one pop up here a few seconds ago. The question is from Brent. I didn't understand your hypothesis of oscillation due to slugs of liquid. And then in parentheses, it says excess charge. Are you suspecting entrainment into the purge line?
Okay, the hypothesis about the pulsation is because of the pressure wave generated within the heat pipe. The pressure wave can be generated by bubbling. If you have because the heat pipe is actually, we test in the gravity aided orientation, we might have a puddles formation within the evaporator, and that can generate some bubbles. And when bubble bursting, it will sending the pressure wave throughout the entire system and causing the flow to be oscillating. Did I answer the question?
No additional comment from Brent on the chat, so we'll keep an eye on it to see whether they or whether he provides any follow-up. No other questions have come in yet. Let's give it a minute or so here to see where we're at.
Okay.
Brent says thank you.
Thank you so much. And by the way, just to follow up on my comment, when we reduce the amount of fluid charge, we see that the pulses amplitude decayed. That is another evidence or some hint about our hypothesis.